No, everyone is here.
Okay. Share. And now, okay. Gidrius, you tell me when. You tell
I
me.
think we can go.
Okay. All right. From beginning. All right. Let me move this away. So last year, I was impressed by electron microscopic images obtained by Montserrat of muscle cells from biopsies of patients with MH. Montserrat applied a staining that revealed glycogen. Muscle, as you know, must control carefully the levels of ATP. Glucose is the source of energy and it's stored as glycogen. Glycogen is stored in granules. In this image of 2 by 2 microns, one can find over 200 granules. According to Montserrat, one can take tens of thousands of like images from one fixed preparation, which means visualizing millions of glycogen granules. Not even getting into what they do in disease, the physiological questions regarding the granules are multiple. Why are they where they are? Is it because there's where they are produced? Is it because there is where they are needed or where there is room? Our long-term idea is to locate them in numbers or density relative to cell structure. How many within the A band, within the I band, how many near triads or mitochondria. So the first thing to this end, which is what I set out to do, was to count them using AI because Montserrat and I thought that that was something AI could do better than a human, even if the human is Montserrat. So the plan today is to present a summary of what I learned, the basic operations of AI, and our first product, a so-called neural network or convolutional neural networks that counts granules. And I see this also as a motivator because the programming developed for doing this has so many facilities that an absolute beginner can, with some practice in programming, can implement a working network after a couple of internet courses. And it's not just the state of the field that is surprising to me, but also the nature. You know, I'm sure there might be thousands of programmers working in secret for Google or the Pentagon, but there are millions working with the philosophy of open code, of sharing and helping. When I started, I realized that I had to learn the basics of the language that AI programmers use, which is mostly Python. So I took an internet Python course, and you know how many students it had at the time I took it last year? 2.5 million students. After that, I took the course on neural networks, and it had 400,000 students, and that was last year. Preparing for this talk, I refreshed the course, and it now lists 1.2 million students. So when you have a class of this size, you have to be prepared. When I was confused, which was most of the time, I would ask my classmates for help. So immediately I would get 50 replies. All were different and some were contradictory. Right? So the presentation will have a first part of about 10 minutes, which may seem unrelated and too simple. And what I will do there is to go over the basic ideas of numerical model fitting. Because the way I see it, AI, and you will see it too, it's just model fitting with its own quirks, with its own jargon, but it's just that. And this will be very basic. So I have to remember to make this visible. Okay, here we go. I will first discuss central values. So consider to begin this group here, which represents 1,000 measures of whatever, brilliance of a star with a very imprecise device. And suppose I don't know anything and I want to estimate the actual value. So I will take a guess and then see how good the guess is by calculating the error, the sum of square deviations. In other words, the error is the sum of the differences between the actual measures and my guess square divided by 1,000. In the graph of guess versus error, I start at some value, say 6, and the calculation yields some error about 2. And once I have a measure of the error, I have a way to improve the estimate, which is conventionally done, as you probably know, by calculating the change in the error when the guess is increased. Here I see that the error increases. In other words, the derivative of the error with respect to the guess is positive. So I use this derivative to correct the guess. Because here the derivative is positive, I will correct the guess by reducing the guess. I will go in the direction opposite to the derivative. Then I get a new guess, and from there, repeat the correction process iteratively. So I wrote a program to do this sequentially, and all these markings are what I got. The correction process went on until a point was reached where no further improvement in the error was possible. In other words, the derivative becomes very close to 0. The process is set to converge. So these are the errors as a function of the guess value. They describe a curve that has a minimum, and that at that minimum is our best estimate of the central parameter, 5 in this case. So now we graduate to a more interesting example. These here are measures Y, which are made at different values of X, a variable X. Say that Y is the cost of an Uber trip and X is the distance traveled. We make a model, we say that the cost is approximately a linear function Y of X. The form is slope times X plus intercept. And to find slope and intercept, I can use the same guess with correction procedure, and I can implement it in iterative form. So for example, here I start with 2 guesses, a slope of 1.4 and an intercept of 6.4. They produce this line. It's bad on purpose, but it is a start. Because there are 2 parameters, I need 2 guesses now. The error is now a function of 2 variables, a surface represented here. And here is my starting point, which is very bad. For the correction procedure, now I have to calculate 2 derivatives. The derivative of the error with respect to the 2 parameters. What I then do is combine the 2 derivatives to constitute a vector called the gradient of the function. And to make the correction, we go opposite to the gradient. This way, the gradient descent is also the steepest way of making the error decrease, the steepest descent on this surface. And that's why they call the method is called steepest descent or gradient descent. Here we can follow what happens when we iterate this method, repeating the process any number of times until it converges to a best estimate of the 2 parameters. And this is also the basis of the current artificial intelligence applications. The usual instrument of AI, artificial intelligence, is the neural network. Neural networks were created way back, I think 50 years or 60 years back. I first heard about them from an instructor of biophysics I had in the School of Medicine in Uruguay, who was coming back from a postdoc at UC Irvine, following 2 of the main drivers of the field at the time, a long time ago. They were Warren McCulloch and Walter Pitts, who worked from the U of I Medical School and the U of Chicago, and had published years earlier the first model of a neuron as a simple logical element that could be arranged in networks. The idea at the time in the minds of McCulloch, Pitts, and my instructor was that they were doing neurophysiology, that these networks were revealing how the brain worked. I don't think that the practitioners of AI now think they are doing neurophysiology anymore. Okay, so now we go into neural networks. Here is a primitive neural network. It's a simplification of a model used by the National Association of Realtors, the NRA, to estimate the fair price of a home. They model it as a function of some features of the home: area of construction, number of bedrooms, zip code representing location, average income level of the neighbors. So I'm simplifying, right? Then they combine with some coefficient these numbers to generate a second set of numbers, thus combining the area of the construction and the number of bedrooms. They construct a variable f that calculates the family size for which the house would be appropriate. From the zip code, they derive a number w for walkability of the neighborhood. Then combining again zip code and income level, they generate a q number for quality, an estimate of quality of schools. Finally, they combine these intermediate functions, f, w, q, to generate a price estimate. The price estimate is conventionally called y hat, to distinguish it from the actual price, which is y. Now, each of these combinations for generating the intermediate variables and the final estimate requires multiplicative factors, the parameters of the model. They are also called weights because they estimate the weight that a given variable has on the final price of the house. So this is a two-layer network. I am here calling the parameters of the first layer A and those of the second layer B. What we do next, or what the realtors do next, is to find the best values of these parameters. And they do it by an identical technique as I described before. They need, say, 1,000 homes that have been sold already, so they know everything about them, the values of the features, and the final price, again, called Y. Then they start from some guesses for the parameters A1 to A5, B1 to B3, and put the formula, the model, to work to produce for every home a price estimate Y hat. Then they calculate the error, the average square deviation between each price and the estimate Y hat produced by the model. And then they calculate, as I explained, the derivative of the error with respect to each of the 8 parameters. With the derivative, they calculate the gradient and the gradient descent correction as before. But here there is a conceptual milestone. I might call it the fundamental theorem of AI. And I explain it with this network where I simplified the number of features of the home to 3, the number of neurons in the first layer to 1, and in the second layer to 1. The point of the slide is to show that successive layers generate, and this here comes a math term, where in math is called function of a function or a composite function. And I need all your attention here. This may be the only essential slide of the presentation. You see how the final estimate, Y hat, is a function of the variable V, and V is generated in the second layer, and it uses a variable U, which is generated in the first layer. In sum, Y hat is a function of V, which is a function of U, which is a function of A1 and the other parameter. And remember, what we need to do to find the best values of the parameters is to calculate the derivative of the error, which means the derivative of y hat, with respect to every parameter. For this, we have to use the infamous chain rule of derivatives, which says that to calculate the derivative of y hat with respect to, say, A1, we first calculate the derivative with respect to V, multiply by the derivative of V with respect to U, multiply that with the derivative of U with respect to the parameter. The AI people realize that there is a backward directionality in this process. In other words, a neural network, as shown here, operates via layers of neurons that pass information from left to right in a forward direction. In contrast, the analysis of errors, that is the calculation of the derivatives for correction of the error, progresses from right to left. They call it backward propagation of errors. The concept of backward propagation organized thinking in the field. It is attributed to the guy, Geoffrey Hinton, a Canadian who still works in Toronto. Hinton generated other concepts that define the field. Unlike in the Realtors Association network that I described, Hinton and others started connecting all the input features to all the neurons. In other words, every input feature is input to the first neuron, the second neuron, the third neuron of the input layer. All the outputs of the neurons are then sent to all the neurons in the next layer. That's what they call fully connected network. Another thing they decided early on was not to care what each neuron did. The variables had no longer a name, only a number, and no particular physical meaning. That and the idea of backward propagation, which streamlined the calculus of error, allowed the use of networks with multiple layers called hidden layers. And Hinton had the foresight, another foresight, of calling the workings of this multi-layer network deep learning. That's where the name comes from. And this gave, of course, an aura of mystery, of sophistication to the field. So now we are going to get into the analysis of images, but I have gone through the main conceptual notes of the field. So I think we can take a little break and see if you have any questions. You want me to go back to some of the points that I made, or what?
I have a question. On these two layers that you have here.
Yeah.
Everybody's connected, and so you earlier had the coefficients were unknown, but the function itself, or the linear function itself, was known. I need how to pass from one level to another.
The form was known. The form of the equation was known. The parameter was not. Right. The parameter is the adjustable parameter.
Right. So in this new fully connected network, that is still true, right?
That is still true, and that will become clearer in the next example.
Okay.
No, but that I don't want to stop you.
So are those functions known or not?
The functions are arbitrarily decided by the programmer.
Okay.
And that's why I was saying that of course, they have enormous experience. These are millions of people who are programming and working, and the papers keep coming with new ways of doing things. And now I'll show some of the ways, These are just the super basic. So, okay.
One other quick question. So anyway, just looking at that figure you have up, So the first set of neurons, layer 1, interacts with the parameters, all the parameters, every
with the,
neuron.
the so-called input. No, no, no,
Right,
these
the
are not the
inputs.
parameters. X1 are
Or
not
the
the
inputs,
parameters.
the inputs,
They
right?
are called the features, let's say, or the inputs.
Right, and then the hidden layer is not a new set of neurons. It's the same neurons, but now they're interacting with each other. Is
No,
that
no,
it?
no, 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 no. They are new neurons. They do new things. They can have different numbers also.
Right.
You know, you can put in, and you will see how flexible this whole thing is.
So in the first layer, those neurons don't interact with each other.
No, no, no,
All right.
no,
All
no. The neuron don't. The interaction is next.
Okay.
They operate in layers. That's the only rigid thing here.
All right.
Okay.
Eduardo, I have a question. At the end, you have to compare basically the white hat with the real number, right?
Yeah, we'll get to the white hat. We'll get there.
Right, but the point the question I have is whether the you can change the parameters, but whether you can change the actual equations to try to fit it.
It's like an equation. Yeah, it's like a very complicated function.
Right, but if you can start to change the function as well, you know, to try to fit it better.
You don't know. Well, you change that if you want to improve the
model.
If you want to improve the model, you are going to have, but then you are changing the model. I just have to explain how a model works.
Right. Yeah. I see.
Right.
I see what you're saying.
Yeah, they even call the hyperparameter to this thing. For instance, how many layers? Those are called hyperparameter because they are not the actual parameter.
Right.
They are changing the model, not the parameters. Okay, so ready to go on. So the networks we will deal with are designed to work on images, to examine images. So here's our cat Nacho. I will build images, or I first learned to build networks for which one present images like this and ask, is this a cat? Yes or no? So networks, they have a binary decision to make. So to begin with, something we kind of all know, what a digital image is. It is a set of numerical values corresponding to light intensities in equally spaced points in space called pixels. If in color, it is usually in a 3-color base. An image is then a trio of rectangular sets of pixels. This high-resolution pixel of Nacho has millions of pixels, but we will start from smaller ones, say 64 by 64 by 3 colors. So that seems small, but it's a total already of 12,288 values, 64 times 64 times 3. The first operation in artificial intelligence is to what is called vectorize or also unroll the images, as shown here, in a vertical sequence of values called a vector. So you here find 255, 231, 42, etc. The red one, the green one, the blue one. This vector, in this case, has 12,228 values. The vector of features or input is usually called X with component X1, X2, up to, in this case, X 12,288. The symbol Y is reserved for the true nature of the picture. Y if it is a cat, 0 if it is Donald Trump. The output of the network, Y hat, which can be right or wrong, will also be 0 or 1. Each neuron of the first layer will combine these input values with 12,288 coefficient and produce one output. So each neuron needs a number of parameters equal to that number of input variables. 12,288. So remember yes?
This is Fred here. Is what I'm getting, let's say, so you want to identify it's a cat. So you go to the first layer, So, you know, when it's the realtors that's doing the house size, number of bedrooms, zip code, you know, et cetera. What are the sort of features you're doing here for an image to distinguish a cat from a mouse? Is eye size, shape of the head?
Yeah. There is a whole chapter in the course that I took trying to answer that question, and you will see the initial. You will see when we do a little bit later. Give me a little bit more time to answer that. The answer is not simple. So let me keep what I was trying to explain here. This neuron is going to be characterized by these 12,280 parameters, which are called W, small w, and I put here W1 to W1 to 288. And I also added a subindex 1 to indicate that these correspond to the first neuron. But of course, the second neuron is different. It has a different set of parameters, and they put a subindex 2, etc.
Eduardo, are these just dot products?
And this is what?
Are these just dot products?
They are
Each
that
function?
product. You will see they are that products. So if we arrange this in rows, we will have what 3 rows, because we have 3 neurons forming a rectangle of values where the width is equal to the height of the input vector, and the height is equal to the number of neurons in the first layer. This rectangular array of values, as you know, is called a matrix, which is what Dirk was referring to. The field of mathematics that deals with operation with matrices, among other things, is called linear algebra, and it defines the product of a matrix by a vector. This product turns out to do exactly the calculation that the neural networks need. It is formulated like here. It's called dot products are the components, as Dirk was saying. It is formulated like here, where the matrix is placed first, the vector second. The product is defined in the following way. You multiply the number in each horizontal place in the top row by the corresponding number in the vector, is 1 by this, add all this product and put the result as the first component of the result vector Z. And then do the same with the second row, multiply this by this, and put the sum as Z2. Until you form an output vector with the same number of components as the height of the matrix, or the number of neurons in the layer. Okay. I hope this was clear. This result, the yellow vector, can then be operated by the second layer of neurons. An operation that can be represented again as a multiplication by another matrix, which characterizes the second layer. The beauty of this all is that computers now have single chips designed for matrix operations. And this is a virtue of the so-called graphic cards. They operate on images, that is matrices, rather than numbers. So now computers work with matrices as all computers used to work with numbers. And that is the only way that power is the only way to understand how they can deal with the huge networks that I'm going to show you next. So I have explained how these inner or hidden layers work, but I still have to explain how the final decision, cat or no cat, is reached. The output from the next to last hidden layer, from the last hidden layer, are collected by one last neuron into a variable Z. So there is one last neuron that makes one variable Z, which is a number that can have any value from minus to plus infinity. Then this Z is used as independent variable of this function that I'm marking here, which is the old sigmoid or Boltzmann. So for any Z value in the abscissa, the ordinate, the function value will be somewhere in between 0 and 1. And the simple convention is that when the result is higher than 0.5, is between 0.5 and 1, we say it is a cat, or y hat equal 1. If it's below 0.5, it is not a cat, y hat equals 0. So this is,
Eduardo,
yep, go.
I'm just going to ask a really technical question. So this is some sort of cumulative distribution function. Is it always like which one do they pick? Is it like, or is it what is there a choice here?
There is a choice. There is a choice. People have used different, they use the hyperbolic tangent, for instance, a popular one. In the end, I'm not sure it matters that much. You can also do a rectified function called ReLU for rectified linear unit, where you put, for instance, instead of the sigmoid, you can put a straight line between here and here, and then 1 all the way to infinity and 0 all the way. There are choices there. But the point is that you need a nonlinear function with a range of the dependent variable between 0 and 1 at the end to define y hat in a binary case. And another point to aficionados is that you need to put a nonlinear function to add a nonlinear function to every layer for reasons that I can discuss later. But that's a detail, let's say. Okay, so any more question here? It's another good point for a break. These are the fundamental ingredients.
Eduardo, I have a question. How you could put other layer of neurons, for example? Like because you could put more layers of neurons, right? You have 3 first, 3 later, and then you could do 3 more.
Oh, you can
right?
have lots and lots of layers.
Right, but what define that which would be the advantage to have more, basically?
That you have more parameters. Those are the ways of incorporating new parameters. It's like making the model more complicated.
Right.
And it has worked. So I cannot argue philosophically, just say that empirically it has worked. It has made possible all the current artificial intelligence.
Right. But if you have more, you would have more precision, or you would have more, for example, to see more details, or there's some correlation between how complex the model is and potentially what would be the output?
They do more complicated things.
Yeah.
Like decisions with more possible outcomes.
Mm-hmm.
For sure. Yeah, that's part of that is coming.
Mm-hmm.
So anyway, I had to make a program with this along these lines to pass the course. And the one I did, I input Nacho here, started reading electrophysiology of this book, and he gave me a y hat of 1. So it was successful in that way. Would write my little program. But this one where Nacho was falling, he does that on purpose because I catch him. Matilde took this picture and my program decided that it was not a cat. So the fact is that these fully connected networks that I explained don't do very well with images. The modern neural networks for images start with layers that work differently and then pass the information at some point to the basic fully connected layer that I explained. So the initial layers do convolutions. That's the name, convolutional neural networks. And even though most of you know what convolutions are, I will present a basic description in 2 slides. Convolutions can be thought for images as filters that modify the images. Filtering uses small arrays of numbers as shown here called kernels, and they are also known as filters. The GIF shows how convolutions actually work. The kernel values are multiplied position by position by the pixel value, corresponding pixel values. The results for the full kernel are added and substituted for the pixel value in the center. As shown here, convolutions may reduce the size of the image. And one can reduce more by skipping over pixels. Reducing size is useful for many reasons, including to deal with these megapixel images like the one I showed. So different kernels do different things. If you think about it, this one, which adds the values of 9 pixels and divides by 9, that's averaging of the 9 values of the underlying pixels. The effect it has is smoothing the image, so it's a smoothing filter. This one is more interesting. So this is an answer, I think, to the question by Fred of how do these layers work and if they do something intelligible. This one marks vertical edge. This is an edge detector, marks all vertical edges in the picture. And the combination of edge detectors, which is available in your smartphone, did this to the image of Nacho falling. Right? This was just done with the phone. So another feature of these networks is that one can use, yep.
On the left, I still don't get, I mean, I understand the convolution is an imaging and, you know, edge detection, smoothing. What I don't get is one has to pre-assign, probably in the first layer, what distinguishes, what are characteristics for one animal versus another?
No.
No.
No, absolutely.
How is
not.
that done?
That's done by the fitting. That's done by the correction procedure. That's the beauty. That's why I dedicated so many slides.
Yeah, but what I'm not getting, I don't understand.
No, because you can measure the error and you can calculate the derivatives.
But what's being calculated, there's some features that again, for example, what are this, just in words, what are the sort of features that are put in that are quantified?
They are not.
Let me interrupt. Does it mean that you need to introduce 10 cats and 10 no cats?
Yeah, it does. It
And
does.
then-
You need to introduce 1,000 for it to work well.
Yeah.
I'm getting there.
Yeah, you need
Okay.
to
It's
train
totally
it on a large
empirical. The whole
data
thing is
set.
empirical.
Yeah, I think, Fred, the answer to your question is you need to train it on a large data set
Yeah.
because everything inside is a black box. It's just parameters and some linear functions at this point.
Yeah, I know they always say, you know, for AI, you have to train it. You have to train the computer.
Yeah, I'll show the training process. This is coming. This
Okay.
is coming.
All right.
This is coming. So what I was saying is that one can use as many different filters as one wants. So here we apply to this image 32 filters. Each resulted in a different image, right? Because the filters were all different. So the images were stacked as layers, and now they are no longer called images, they are called channels to form an output volume. And you have to keep in mind, again, I think this was a question by Jose, why we are doing this. What we are building a model with adjustable parameters. So filters introduce new parameters. Simple question. I know you can answer before our final push. How many parameters did this layer introduce if it consisted of 32 filters of 3 by 3? The kernels were 3 by 3. How many parameters did I include here? The answer is 288. 32 times 3 times 3. So every little number there is a new parameter. Okay, so can I go on? No answer means yes. So this slide illustrates the network that I put together to solve our problem with Montserrat, the counting of glycogen granules. And it also shows how convolutional networks are assembled in general, because I just followed some recipes. So this is an image where I want to count granules. It is an array of 256 by 256 by 1 value. Being grayscale, it has only one color. It is passed, as I said first, through a filter set that reduces the size to 128 by 128. That is done by skipping every other pixel. Because I have 32 different filters, the output of the layer is a 32 image deep or channel deep volume. Then I added more layers of filter, following again general recipes. I didn't fully understand what I was doing. And at some point, the convolutional part of the network ended. And this volume of information is passed to a regular fully connected network like the ones I explained before. First, you vectorize all this, form a vertical vector, and then you pass it through the fully connected part of the network and you take it to a final decision. An interesting aspect of this network is the volume of information that they handle. The information passed to the fully connected part, for instance, is contained in this last volume. And this last volume consists of 32 by 32 by 16, or 16,384 numbers, which means that every neuron of the first layer of the regular network will need 16,384 parameters, or the weight, the small w's that we talked about. Because this layer has 1,000 neurons, it contains 16,384,000 parameters. By comparison, the convolutional part is much lighter on parameters. We just saw how this stage has 288 parameters. My neural network, which is somewhat simplified here, ended up having 25 million parameters. And that, by comparison with current networks, is modest. Current networks may have hundreds of millions of parameters, and the computers can handle that. Okay, so how did Montserrat and I finish the project? And remember, once we have a network, its parameters must be fitted to a set of images for which we know the answers. You have to fit the model. In AI jargon, as we were saying, the models has to be trained. So training is model fitting. We got from Montserrat another large image. We love this one. Look at the non-junctional part of the transverse tubule here, versus the junctional part. Is amazing. So this is again 4096 by 4096, about 2 micron on the side. And Montserrat put markings identifying granules. So we divided the image into smaller sub-images of 256 by 256 pixels. This is the one I showed in the example before, for a total of 256 images for the training set. So here I am showing only the one derived from this part, from this rectangle. This subdivision is done for 3 purposes. One, of course, was to have a set, a training set. And another was to simplify the task. If you look here, you will see that no sub-image has more than 9 granules. So the network let's simplify the task of the network. The network has to decide between 10 possible counts, 0 to 9. And I've shown how the model makes the binary decision, 0 to 1, cat or no cat. But how does it count from 0 to 9 in this case? It turns out to be quite simple. Remember that the final neuron makes a combination of all the outputs of the next to last layer. That number, Z, is then used as independent variable of a sigmoid. And the dependent value, as we said, will go from 0 to 1. So in this case, we divided, in the binary case, we divided the output variable in 2 intervals, the range of the output variable in 2 intervals. For this purpose now, I divided it into 10 intervals of 0.1 each, and assign, as you would expect, each to a count between 0 and 9. So now you know everything, but we have to see how the model did, or how the neural network did. Then we go into testing the model. Testing the model is the complement to training. You train and then you test until you have a working model that you can use. And you can imagine by now how we proceeded. Montserrat again sent another large image with granules identified. We subdivided it as before into 256 small images and fed all of them one by one to our model. Now the model was trained. It had best fit parameter that it couldn't change. The only thing the model could do was count in every one of these images. So how did it do? It found the right answer, y hat equal y, in 70% of the input images. So 70%, you might say, is not a big success rate. So anyway, considering that there are 10 possible outcomes, if a chimpanzee was choosing the answer, the expected success rate would be 10%. So the model improved on the chimpanzee by a factor of 7. We were quite happy. Another point that I have not shown them to Montserrat, but on close examination of some of the images, some of the supposedly wrong answers look actually better than what the human user had counted. We'll see about that, Montserrat. And the final point is that the model read the images and produced the answer in less than 1 second. So that's all I have. Montserrat was crucial, as I said. The human preparation were collected by the Toronto team of Sheila Riazi. Also in Toronto, Amira Clip taught us everything we know about glucose metabolism and kept pushing us. And of course, this is the local team. I have to say again that Carolina was who long ago started the malignant hyperthermia project, and Ishwar made us turn to the study of its biochemistry, and Carlo is the one who makes every project work. So anyway, that's it.
So if you train your program better, like you said, you're training the program and then you're getting this 70%. If you train better, like longer, so it will be more than 70%?
That's excellent. That's excellent. Yeah, the actual success rate in training the model was 100%.
Yeah.
In other words, you train the model until the error is practically 0, right? So it is true that the more, what happened then is that even if in the training set it is 0, when you go to an unknown, to a set, the testing set that is unknown to the program, in the sense that it was not seen before, you get usually a worse result, right? But the training process can be perfect. And of course, I think that the more you put in the training process, the better success will then be had with the testing, right? But yes, it's a good question.
One other thing could be to try different combination of the filters.
Oh yeah, but the filter, you don't change the filters. The only thing you can do is change the numbers of filters. You know, in other words, you change the model. It's like changing the structure of your formula when you have an analytic model. You know, it's like instead of fitting a square line, you can fit a parabola or a hyperbola, or it's analogous. You can add more layers. That's like you're adding a bunch more parameters. And this is an interesting anecdote. So I was calculating the number of actual variables. It has to do with the number of pixels that you have in a, you multiply 4096 by 4096, the number of pixels in these images that we used for our purposes. And that's 16 million or so, right? So I asked one of my instructors, how can a model of 25 million be used for fitting 16 million pixels? You know, it looked like this thing was over parameterized to death. And he had no answer. He hadn't looked at it from there. And he was so taken by the question that he started collaborating with us. But then what I saw was that I had to reduce the number of, I was removing layers to get to the 70% success rate. So the actual working model that I have has something like 12 million parameters. I didn't tell you that, not to complicate the issue, but that was a fact. So there is a point where you are over parameterizing for sure.
No, and another natural limitation, difficult to deal with, is if you cut a glycogen granule. Because if you have a quarter of a granule, like let's say one that falls in the cutting of 4.
Oh yeah.
That is also a complication.
This is part of the noise of the system, you know. It's true, you know. Yeah. You can see it here. I think I'm still sharing, right? So you can see here, these things are cut. So but we have no control over that. It's part of the error. And I mentioned also, I said that we did the subdivision for 3 purposes. One purpose was to have a training set. Another purpose was to simplify the task for the little brain, which was to count, but only between 0 and 9, right? So the third purpose was that in a way, we are already locating. Remember, the long-term project is to locate the granules relative to the structures, right? For instance, here is a triad, and here is a very dilated, shame on you, Montserrat, cisterna of the SR. So we, and here are myofilaments. So we wanted to know the position of the location of the granules. So this in a way start to locate the granules because these are 2 by 2 micron. I'm sorry. This is a 2 by 2 micron image of this. divide the elements in 10 nanometer or so, 20 nanometer positions. Or maybe I'm calculating wrong, I don't know. So in a way, we are already locating the granule, already have information on location. We are in a way into that, but the thing that we now have to do is to train neural networks to locate triads or to locate the Z disk or to locate the A band, etc. That's not done. Okay, I'll stop sharing if you want.
I just want to go back to Ruben's point about the training. Yes, more training is always better, but you run into the problem of the data set that you're comparing to. You have to know what the right answer is. So that is one of the biggest problems, is getting good training set data for any AI, because the answer has to be right. And that involves generally a lot of labor. Like in this case, like counting little dots, you know, is I imagine that some poor person had to do this to count all the dots in these pictures. And so that's labor intensive, and that's one of the things that is holding back AI, is having good quality training data. And this is also why AI has difficulty with recognizing people of different races in facial recognition, because there isn't enough. One of the reasons is there isn't enough data sets that have like people of color who are a relatively small part of the population. So in a lot of these training sets, makes those people, basically the training set for people of color, much smaller than other groups. And so, which is why it does better with white people. One of the reasons that it does better with white people.
Mm-hmm. True. But our problems are a little bit less than that, than those.
Right, but somebody still has to sit down there and count the dots, which is, you know, not fun. And if you do it for an hour, you're going to start making mistakes. And so your data set.
But just with 2 images, look what we could do with 2 images. We got 70%.
Yeah, no, I think it's great. I'm just trying to.
How long did it take?
Question as to what the limitations are. It's like, yes, you want more training, but that means a lot of work.
Right, Montserrat. How long did it take you or?
No, I did it. It took maybe, I mean, for this case, it took 10 minutes. But when I am doing the single particle in the past, when we didn't have automated programs, I would have to be there. I think once I was there for a month. Yeah.
No, but for these two images that I show, how long did it?
No, 10 minutes each or something like that. Yeah.
Yeah, but if you want a significant training set and you want to do 100, you know, or 1,000, then that 10 minutes starts being multiplied pretty quickly. And that was my only point. I mean, I'm not saying anything bad about your result. I'm just talking about training in general.
No, but now like an example for the single particle projects where we have 10,000, at least 10,000 image of 6,000 by 8,000 pixels. We only pick manually in one morning 1,000. And then the automated particle picker will pick 500,000 in one day.
Right.
It will do it for us. So it's well worth the investment. That's what I mean.
Oh yeah.
Yeah.
Definitely.
And you are right about the representation. I mean, but that would happen with humans too. I mean, yeah, if you have less sampling, the probability to recognize it will be lower. Yeah.
Yeah, I mean, for the analogous thing for you, maybe you have fainter dots and really black dots, you know, that it would be easier to pick out the ones with high contrast and not the ones with low contrast. And that may be part of your error. And if you had more data, more training sets, then it would help pick those up. But I think what you guys have done is really cool. And after this presentation, I actually sort of feel like I understand this AI stuff, because it was always just a mystery to me. Although it's a mystery to me as to how you can get away with only doing matrix vector multiplies a cajillion times and get a good answer.
No, you can't do that. I kind of said it, that, I didn't want to dwell on it, but here is the point. You need to have a nonlinear function after every matrix multiplication. In other words, every neuron has a little thing at the end that is nonlinear. Sometimes it's a very simple rectified linear function called ReLU, which goes for rectified linear unit, and they are very important. They are essential. And you will understand right away, or anybody that has worked with matrices will understand right away why. Because you multiply 100 matrices by each other and you end up with another matrix. So you haven't added anything, right? So if you keep multiplying matrices, what you get is another matrix. You do the associative of multiplication and you get another matrix. So you need to have something in the middle of every matrix multiplication to prevent those parameters to become one, That's I know it's confusing, but that's why I didn't want to say it in the middle.
So those nonlinear functions are picked by the user, right? They're not
picked by the user, but they are traditional.
Yeah.
The one that is more popular is the ReLU. The ReLU is just a linear function that is at when it intersects the horizontal axis, it becomes zero. It's like a rectifying channel.
This is one of these things I find really fascinating, is like all these really complicated, sophisticated algorithms and stuff. At the end of the day, a lot of it is just linear stuff.
It's incredible.
It's just linear stuff.
And the one that is not, and the thing that are not linear, nobody knows.
It's pretty close. I mean, if it's a cutoff,
and they are not important, and the details are not important.
Yeah.
So the magic is in the correction. That's why I made this a kind of very elementary introduction to the talk, because the magic is there. It's the correction of the error. It's a systematic backward, as Geoffrey Hinton said.
Eduardo, is there any non-reference classifier, like any classifier that doesn't follow any reference, any human input, just plain classification?
I don't know enough to answer. The only thing I've read is need the human input first. No. Okay.
Eduardo, I have a question. So, for example, when you get more data, then you can go back and try to refine the judgment, the model again. For example, because you have.
Oh yeah, you can infinitely, you can refine it, but the refinement means either training it better, but at some point, if you I don't know, I haven't enough experience to know, but it reaches to a point that the benefit is very small, and then you can change the model. I didn't explain here that convolutional model have many varieties. So the one that I ended up using is called a residual network, ResNet. And in the residual network, you do another trick. And then I mentioned it just as an example that the thing is richer than I presented. You can skip layers with information. In other words, the output of a layer, you can feed it forward, like skip 10 layers. And that's called a residual network because for some reason, funny reason, it's called a residual network. The thing in the middle becomes a residue. So you have one pathway, which is the linear forward pathway, and then you have a skipper. From the same layer, you go 10 layers forward and you feed the layer 11 with 2 inputs, one from the right pathway and the other one from the skipper. And that's called a residual network. And so that has permitted much deeper network. Right? So that's where you get 200 million parameters.
Oh.
That's how I got 25 million parameters, by using residual network. And so like that, there are new innovations that come every 5 years, comes something really revolutionary. And another point is that the paper that described for the first time residual networks has 150,000 citations, and it's only in 3 years.
Yeah.
And compared with the volume of people working in our little biophysics, this thing is huge and is moving very fast. And the other consequence that that has is that there is a lot of facilitating nested programming environment. So you start with Python, right? But Python has a whole subset where all these derivatives are calculated for you, and all this backward, you don't have to follow every coefficient. It would be impossible. And that's called, the popular one is called TensorFlow. Because these are tensors. If you look at them, they are 4-dimensional volumes of information. So it's a tensor. And it flows and via a subset of Python that it has completely compressed language, simplified language, that allows you to do all that. It's called TensorFlow. And then TensorFlow has now a subset called Keras, right? Keras, and I don't know why. It's called Keras, but that's even more compression. So to give you an example, the final program that I wrote, the final network that I wrote that takes the input and gives you the answer, white hat and all that, had maybe 20 lines of code. They were complicated lines, but they were 20 lines of code. You know, for anybody who does some programming, I mean, what to do with that? It's interesting in that sense. And that's the beauty of having a few million people doing the same thing. Also, most of them are in China and India. So all this idea that the Chinese are taking our ideas and stealing and using and free, how do you say, freeloading is not true.
But
Completely
2/3
not
of the
true.
world's population are in China and India.
No, but I mean, there is this mythology that the Chinese are freeloading, right? They are taking our creativity from the US and in the West. No, it's not the case. Not in artificial intelligence.
Sometimes they do, sometimes not. It
Okay.
depends where. Yeah.
All right, bye all. I gotta run.
Thank
Eduardo,
you.
before you go, I
Yeah.
just want to have a quick one thing. I didn't want to. I don't know. Sorry, everybody's not leaving. I didn't want to say anything. It's generally pronounced kernel, not kernel.
Okay, good.
It's just the emphasis is on the wrong syllable.
Yes. Thank you.
But like I really found this interesting, and I really actually learned a lot. And so thank you very much.
So that's why
really,
I said beginner.
Yeah.
Like when I studied kernels, I did it in the School of Engineering in Uruguay, where we just said kernel. Okay.
My thought was kernel too.
Yes. Yeah.
Bye, guys.
Okay.
Okay, thank you
Bye,
very
Eduardo.
much. Bye,
Thank you,
Eduardo. Bye,
Thank you.
everybody at Chicago.
Yeah, pleasure to see you.
Oh, it's great to
Bye.
see you, Montserrat.
Bye.
Yeah.
Oh, this was recorded. Okay, so whatever you said is there.